Greetings. Welcome to today's class. So in the previous class, we were looking at root locus. We learned about the construction of the root locus. We also looked at how one could essentially use the root locus for control design by doing an example where we used the knowledge of the performance characteristics that are desired to essentially get the range of controller gains. All right. So that's something which we discussed in the previous class. So in today's class, we are just going to discuss a few more cases, and then we will see how the root locus can be used for control design in general. Okay, so we'll look at that overall discussion. So what I am going to do today is to start with a discussion on how to design the root locus when we have positive feedback. Okay, so that's something which we will get started with. We will first discuss how we shall draw the root locus or construct the root locus with positive feedback. Then we will look at why we are doing it. Okay, so the intention will become clear, right, as we go on. All right. So once again, let me draw the basic block diagram of the closed loop feedback system. So we have the reference input, we have the forward path transfer function, which will give us the output, and we have the feedback path transfer function, H of S, which will give the signal W of S. Okay. And this is the error E of S. The difference here now is that we have positive feedback than negative feedback. So we can see that at the summing junction we are adding, right, rather than subtracting the two signals. Okay, sorry about that. Okay, so recall that for the positive feedback closed loop system, the closed loop transfer function is going to be y of s by r of s. That's going to be equal to g of s divided by 1 minus d of s h of s. Okay, so that's what we are going to get. Okay, as the closed loop transfer function of the positive feedback closed loop system, right? So consequently, the closed loop characteristic equation is going to be the following. So the closed loop characteristic equation is 1 minus g of s h of s is equal to 0. Okay, so that's the change that we have, right, as far as the closed loop characteristic equation is concerned. Right. So now the question becomes, what will happen, right? So with this particular closed loop characteristic equation, right? So we rewrite once again it as g of s h of s equal to plus 1, right? So obviously, as we already know that any value of s that satisfies this equation is a closed loop code, right? So once again, please note that we have written in terms of the open loop transfer function. So as we go forward, we will realize why the open loop transfer function is a useful entity, right? So we define this open loop transfer function, right, as W of S by E of S. Okay, so we will keep on encountering that many of the methods that we are going to learn will be based on the open loop transfer function. So it's a useful construct to have. So any value of s that satisfies this equation is a closed loop code. Okay, so that is the impact of this particular equation. Okay, so now what we can do is that once again we can rewrite this as two equations, right? Just like what we did. So if g of s h of s equals 1, then the magnitude is 1, Now, the main difference is that the face of g of s h of s will be an even multiple of 180 degrees or a multiple of 360 degrees. So, people will typically rewrite like this: 360 times k being 1, 2, 0, 1, 2, and so on, right? So, this is the magnitude condition now, okay? And the second equation is the angle of the phase condition, okay, in this particular case. So, consequently, any value of S that satisfies both these conditions is a closed loop once again. Okay, the same statement holds for even these two things. Okay, so once again, we shall consider the g of s h of s, the open loop transfer function, can be written in this form: k times s plus z1 all the way till s plus zm, okay, divided by s plus t1 all the way till s plus tn. Okay, and we shall consider the case where k is positive, right? So k is greater than 0. Now the question that arises, we are going to ask ourselves is that, like, how do we draw the or construct the root locus for this particular case? That is, when we have a positive feedback and we have this scenario where the open loop transfer function is we take it to be representable in the same structure as before in terms of open loop poles and open loop zeros. The main difference being that now the phase condition is changed, right, from an odd multiple of pi in the first set of steps that we have learned to an even multiple of pi. Okay, so let us go through the changes in the steps, right? So, I'm going back to the same document where we looked at as far as the root locus construction of concern. So we are considering the same structure as far as the open loop transfer function. As we know, the main difference now is that, like, we have got this minus, right, in the closed loop characteristic equation, right? Because the closed loop characteristic equation now is 1 minus g of s h of s equal to 0. So if we look at the steps uh, as to what will change, like as far as the root locus is concerned, right? The steps that involve the angle condition, right, would change. Okay, so as far as the root locus is concerned. So if you look at the first step, let's go one step at a time, right? So if you look at the first step is to locate the open loop zeros and open loop poles in the complex plane. That's not going to change, right? Is it right in the second set of steps? The second step will be to locate the root loci that lie on the real axis. So previously we took a test point and we looked to the right of the test point, and then we counted the number of real open loop poles and real open loop zeros that lie to the right of the test point. And if the count was odd, we said that the test point lies on the root locus. Now, since the angle condition is changed to an even multiple of pi, we can immediately see that we follow the same thing. We choose a test point. Okay, we count the number of real open loop poles and real open loop zeros to the right. Okay, that's the count still we do. But then you can immediately realize the difference, right? So now this count should be even, right? Then that point lies on the root locus. Okay, so that is what I say, an important difference. Okay, so you can immediately see that step 2 changes. Okay, when we consider this set of steps. Okay, for the constructing the root locus with positive feedback. Now the step 3 will be to determine the asymptote. So the angle made with asymptote previously was 180 degree times 2k plus 1 divided by n minus m. Now you can immediately observe that it has become 360 times k divided by n minus m. Okay, so this is the change. All right. So you can immediately get a feel of what is happening, right, as far as these steps are concerned, right? That's the difference in step 3. Step 4 remains the same: breakaway, break-in point. They are what they are, right? So we apply the condition and see whether we are able to solve the roots for that equation b prime as a of s minus a prime as b of s, and then, like, calculate the all possible values of k. Then we see whether K is positive or not, right? So that step still remains same. There is no change. Step 5 changes. If you recall, we talked about angle of departure from a complex open loop pole and angle of arrival at a complex open loop 0, right? So previously, this step had 180 degrees, right, in the formula for calculating the angle of departure and angle of arrival. That was once again based on the fact that we used the corresponding angle condition, right? But however, now the angle condition is changed to an even multiple of 5. So immediately you can see that this 180 degrees has been replaced by 0 degrees. Of course, we can write it as 360 degrees also, absolutely no problem. But then like we have 0 degrees as the replacement, right? So in this particular case, so you can see that primarily, like when we go for this case, that is like the second set of, let me call this a set 2 of the root locus set. The one main change is that like we have positive feedback. Everything else remains the same. Okay, K is still a positive real parameter, right? So we can see that the main changes are in steps 2, 3, and 5. That's because those are the steps that use the angle condition, right? So that's what we have. All right. I hope these changes are clear. Anyway, we are going to rework the same example with positive feedback, and we shall see what are the changes that come about. Okay. So let's do the same exercise. Okay, where the open loop transfer function was g of s h of s equals k divided by s squared plus 4s, k greater than 0. Now plot the locus of the poles with positive feedback. Okay, so the question is plot the root locus with positive feedback. Okay, we did the problem when we had negative feedback. Now we are going to do with positive feedback. Okay, that's the change. So let's work out through the entire exercise. So this will also serve as a refresher for us as far as the steps regarding plotting the root locus is concerned. So if you are asked to plot the root locus by hand in your homework or exams, you just need to follow these steps, okay, in a very sequential manner. That's all you need to do. So let's run through each step. So step 1, right? Step 1 is to locate the open loop poles and open loop zeros on the in the S plane, right? So that's what step 1 is. So if we are locating them on the S plane, let's first construct the S plane. So this is our origin. This is the S plane. You need to label all the axes on the plane also, right? So if we do that, once again, the poles, open loop poles are at -4 and 0, right? So this will be the start of the root locus as k tends to 0, right? So that's something which we know, right? So to go in a very methodical way, so please note that the value of n is 2, the value of n is 0, and the open loop poles are at 0 and -4. Okay, there are no open loop zeros in this particular case. Okay, so those are two important observations that we can make. All right. Okay. So this is step 1. Okay, let me write these steps in red color so that they are clearly identifiable. Okay. Step 2 is to essentially locate which part of the root locus lies on the real axis, or sorry, the other way around. Sorry about that. The second step is to locate which portions of the real axis lie on the root locus, right? So that's the second step. So once again, what we do, we essentially take test points, okay, in the various regions and then test them, right? So you can immediately observe that there are 3 regions formed by the open loop poles on the real axis. They divide them into minus infinity to -4, -4 to 0, and 0 to plus infinity, right? These are the same as before. Now, you take a test point ST1 in the region -infinity to 4. We look to the right of it. We can see that we count 2 real open loop poles and real open loop zeros. We need to add, right? But in this case, there are no open loop zeros on the real axis. So that is why we are only looking at the open loop poles alone, right? So that's about it, right? So essentially this number is even. So now you can see that the region minus infinity to 4 is on the root locus, okay, point number 1. Now if you take a test point between -4 and 0 and look to the right of it, we can count only one real open loop pole, right, to the right of it, and no real open loop zeros, right? So that means the total sum is odd, which means that in this case, sorry, this region -4 to 0 is not on the root pole. Okay, so that is the interpretation. Then let's say we take a test point ST3, the region 0 to infinity. We look to the right. Then we see that there are no real open loop poles and no real open loop zeros. Right? So the sum is 0. This we take it as a positive result in this case. So the region from 0 to infinity lies on the root locus. So you can immediately see that we are getting complementary results, right, compared to the previous case. So due to this, we immediately observe that our root locus will start off something like this. So it is going to start from -4 to the left and from 0 to the right. Okay, previously it was the other way around. The reason for this trend is because, as we already argued, since we have a non-repeating open loop pole on the real axis, there can be only one branch. Obviously, that branch cannot go on the complex plane, right? It has to go on the real axis. So the branch from -4 can only go to the left, and branch from 0 can only go to the right, because based on step 2. All right. So that is the idea. So now moving on to step 3. Once again, please stop me whenever there are any questions. Okay. So let's move on to step 3. So we can immediately see that once again there are going to be two asymptotes because n minus m is 2, right? So excuse me, there are two asymptotes. So the angle made by the asymptote is going to be equal to, we are going to use the modified formula, which is going to be equal to plus or minus 360 degrees times k divided by n minus m. In this case, n minus m is 2. So immediately we will get 0 and 180 degrees, right? In this case, n minus m is 2. Okay, so that's what we have. All right. So what it means is that, like, I am going to have two asymptotes, one along the direction of the positive real axis and another along the direction of the negative real axis. So, but now what happens to these? Okay, where will I go for these, right? So how do I locate them? So that we can have by looking at the point of intersection. Okay, of the asymptote. So how do we get the point of intersection of the asymptote? The point of intersection of the two asymptotes can be obtained by using the same formula. That is sum of open loop poles minus sum of open loop zeros divided by mn. Open loop poles are at 0 and -4. There are no open loop zeros, and divided by n minus m, we have 2 minus 0, right? So the point of intersection is -2. So what it means is that, like, the two asymptotes need to intersect at -2 on the real axis, but their angles should be along 0 and 180 degrees. This means that the negative real axis and the positive real axis are the two asymptotes. Okay, that's it, right? So one asymptote means that this will go along this direction and this will go along this direction. So this is the direction of the asymptote. Okay, so let me reason out once again. So there are two asymptotes which make an angle of 0 and 180 degrees. So I can't have one asymptote like this and another asymptote like this, right? I can say they make an angle of 0 and 180 degrees as it tends to infinity, but they don't intersect at -2, right? The fact that the asymptotes intersect at -2, what to say, leads to the only choice that in this particular case, the two asymptotes must be the positive and negative real axis themselves. So I hope the argument is clear, right? So that is what we have, right, in this particular case. right? I hope it's clear how we have reasoned out what the asymptote is. Right? So, okay, so moving on, let's move to step 4. If we look at step 4, what is step 4? Like we need to look at the breakaway break-in point, right? So once again, we write A of s. A of s is 1. B of s is s squared plus 4s, right? A prime s is going to be 0, and B prime s is going to be equal to 2s plus 4, right? So those are the main quantities. So we use the same equation, right? So B prime s A of s minus A prime s B of s is equal to 0. What will this give us? This will give us 2s plus 4 multiplied by 1 equal to 0. Okay, so because the second term will be 0, since A prime s is 0. So this will give s to be equal to minus 2. Okay, we still do not know whether this is a breakaway point, right? So we need to test whether this can be actually a breakaway point, right? So what will happen? What we need to ascertain, right, is that what is the value of k, right, at this particular value of f, right? So as we know, the closed loop characteristic equation in this particular case can be written as 1 minus k times A of s divided by B of s. This means that k for positive feedback will be B of s divided by k of s. Previously, it was minus B of s divided by A of s, right? Was it not? In this case, it will be B of s divided by A of s. So, if we evaluate k at s equals minus 2, what we will have is that, like, we will have B of s by A of s, which is 2s plus 4 divided by 1. The whole thing evaluated at s equals minus 2, and we will get the value as minus 4. Sorry, not 2s plus 4. Okay, this should be s squared. Sorry, this should be s squared plus 4. I wrote b prime. Okay, so if we evaluate at s equals minus 2, we'll get minus 4, right? And this is a negative number, right? But we are starting with with the problem wherein we have k to be positive. So this means that in this case, s equals minus 2, although coming as an solution to that equation b prime as a of s minus a prime as b of s equal to 0, it is actually not a breakaway or a break-in point because of this. The value of k at that point is negative, whereas k should be positive. So this implies that in this problem with positive feedback, although the system is the same, the only thing we changed is that, like, it is positive feedback rather than negative feedback. There is no breakaway or break-in point. Okay, so that is what we can conclude, from this result. Okay, because k was supposed to be positive, we got a negative value of k. That means that consequence is that, like, there cannot be any breakaway or break-in point. Okay, with positive feedback. All right. So that's step 4. Now moving on, what is step 5? Step 5 is angle of departure and angle of arrival, right? So in this particular problem, this step does not apply. Okay, why? Because there are no real complex. Sorry, not there is. I should repeat it. Step 5 does not apply in this problem because there are no complex open loop poles or complex open loop zeros, right? So angle of departure and angle of arrival are meaningful only when we have complex open loop poles and complex open loop zeros. Since we do not have them in this particular problem, that step no longer applies. Okay, so that is something we need to remember. Alright, so step 5 is not apply. So going ahead to step 6. So what is step 6? We need to find the crossover point. So for that, we once again look at the closed loop characteristic equation. Please note that in this case, the closed loop characteristic equation is 1 minus k times k divided by s squared plus 4s, right, equal to 0. So this will give us s squared plus 4s minus k is equal to 0. What we do is that, like, we substitute s equals j omega in this, we get minus omega square plus 4 times j omega minus k equal to 0. So this will give us two equations, right? Minus omega squared minus k equals 0, that comes from the real part. And then 4 omega equals 0, that comes from the imaginary part. So if we use both these equations, what we have is the following. This implies that in the second equation, omega equals 0 and k equals 0 at that point. So in essence, there is no crossover point other than the origin. Okay, sorry. Okay, so that means that s equals 0 is the crossover point. Anyway, that is the open loophole. So what it means is that, like, the root locus does not cross the imaginary axis for any point other than when k tends to 0, right? So s equals 0 is the crossover point when k is equal to 0. All right. So that is the result, right? The end result. So now, so if we go back using all these steps and look at the root locus, this is the root locus. That's it, right? One branch starts from -4, goes to the left as k tends to infinity. Another branch goes to the right, starting from s equals 0, right? That is another open loophole, and goes to infinity along the positive real axis as k tends to infinity. That's about it. Those are the two branches in the root locus, right? So we have constructed the root locus, right? So for this particular system with positive feedback. Okay, once again, I can't re-emphasize this enough. So, we are looking at positive feedback. So now, what can we conclude from this? About the stability of the closed loop system. Just by looking at the root locus, do you think the closed loop system can be stabilized using positive feedback?
No.
No. Why not? Correct. No is the correct answer. So you can immediately see that one branch of the root locus is always in the right of plane, right? For any k greater than 0. So that means that one closed loop pole is always going to be in the right of complex plane, right? For this closed loop system. So there is no way we can stabilize the system, right? With positive feedback. So it can be observed that the closed loop system cannot be stabilized.
It means for all conditions, right? Or only for the specific condition?
1 minute. Let me explain. Just a minute. Cannot be stabilized for any k greater than 0. Right? That's it. That's the subcondition. Okay. So now coming to your question, right? The point is, if you are given the system with positive feedback and k greater than 0, it cannot be stabilized. So let us now look at the closed loop characteristic equation. Right, this is 4 s squared plus 4 s minus k equals 0, right? So when do you think the closed loop system will be stable with positive feedback?
K is negative.
K is negative, right? Because if you apply the Raoult's criteria for polynomials till order 2, all coefficients must be of the same, must be non-zero and of the same sign, right? So we can immediately observe that the closed loop system would be stable for k less than 0. Okay, so that is the consequence. Sorry. Okay, so that is the consequence. I hope the point is clear, right? So when will the system be stabilized? So once again, please let me recap what we have been doing in this particular class. we took the same example as we looked at before as far as the open loop transfer function was concerned. What we did was that like we just instead of negative feedback, we essentially looked at positive feedback, and we saw what are the changes in the steps of the root local, and then we realized that with positive feedback, the closed loop system is not stable for any value of positive k. But however, with positive feedback, the closed loop system is stabilized for negative k. Now, the follow-up question is that one may immediately ask the question, how does one construct root locus with when k is less than 0? Right? Isn't it? I'm sure all of us will get that question, right? So how does one construct the root locus when k is less than 0? So let's reason out the answer, right? So let us consider, let's reason out all the cases, and then like we will find a generic way of plotting root. Okay, let us first consider negative feedback. Okay, but now with k less than 0. Okay, so what's going to happen is that with negative feedback, as we already know, the closed loop characteristic equation is 1 plus k times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn equal to 0. Okay, but here now the catch is that k is negative, right? Yeah. Yes. Any questions? So k is negative now, right? So now what we do is that like let's define a variable k hat which is minus k. So then what do you think will happen? I will have this closed loop characteristic equation being converted to 1 minus k hat multiplying s plus z1 all the way till s plus zm divided by s plus p1 all the way multiplying s plus pn equal to 0. Okay, but the main thing is that now k hat is greater than 0, right? So I hope you understood the difference, right? How we have manipulated the sort of like or transform the closed loop characteristic equation, right, in this form, right, by looking at the by a simple transformation, right? So that is like we just took the closed loop characteristic equation of the positive negative feedback system, and then like we just looked at a simple transformation of having k hat to be equal to minus k, and we ended up with sort of like a pseudo positive feedback system, right? So you can observe that although it is a what to say negative feedback system, we have sort of ended up with a pseudo positive feedback system. So what we do is that like we apply the set of steps that we learned today, all right, by treating the system as a pseudo positive feedback system, but with a positive k hat. Okay, so that's what we do. So we apply the steps that we learned today, okay, to plot the root locus when we have negative feedback with negative k. Okay, so now one can have the other condition also. So let us consider positive feedback with negative k. That is also possible, right? Isn't it? So you see, in today's case, what we did was that like we considered positive feedback, but with positive k, right? So essentially, we had we consider the complement, right, where we have negative k, okay, being this one. So if we recall with positive feedback and positive k, the closed loop characteristic equation was this 1 minus k times s plus z1, sorry, s plus zm divided by s plus p1 all the way till s plus pn equal to 0. So we do something very similar, right? So what we do is that we have k hat to be equal to minus k. What do you think will happen now? This will now become 1 plus k hat. Okay. s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn equal to 0. But now the caret k hat is greater than 0. So this is sort of a pseudo negative feedback system, right? With a positive k. So what we do is that positive k hat, sorry, not positive k, pseudo negative feedback system with a positive k hat. So what we do is that like we apply the set of steps that we learned previously, okay, what I called as the first step of steps, right? Which we applied, which we learned previously, and we essentially look at the root local, okay? But that k hat becomes the what to say parameter of interest, okay? So we can see that what we have learned is quite generic. So if I were to summarize, I would do like this. So if we have, let's say, negative feedback, okay, as a sort of a grid, we summarize what step of steps should be used under which condition. So depending on the type of feedback and the sign of the parameter which comes in the open loop transfer function, we have different scenarios, right? So let me draw it in the form of this grid so that it's clear to all of us. So negative feedback with a positive k is what we learned before, right? So I would say use the first set of steps. That's it. Okay. So positive feedback with positive k, we use the second set of steps, which we learned today. Okay. So what do I mean by first set of steps? So first set of steps means this one. Okay. So this is set one. What we learned previously, we will call as set one or first set of steps, right? Wherein the angle condition was an odd multiple of 180 degrees, right? The second set of steps is what we learned today, wherein we had positive feedback with positive k, right? So that is set 2, right? The second step. So going back to this grid, when we have negative feedback with positive k, we look at the first set of steps, and then like we essentially do the problem. Okay. So then when we have positive feedback with positive k, we use the second set. Now when we have negative feedback with negative k, what we do is that we define k hat to be equal to minus k to get a pseudo positive feedback system. Okay. And then use the second set of steps with positive k hat. Okay. So that is the difference. All right. So once we start doing problems, things will become clear. All right. So how this is done. So once we have a negative k with negative feedback, when we substitute k hat to be minus k as we see above, we get a pseudo positive feedback system, right? As we have already observed. So we do that. So we use the second set of steps. So similarly, when we have positive feedback with negative k, once again we define k hat to be equal to minus k, and we get a pseudo negative feedback system. So then we use the first set of steps, okay, with positive k hat. All right, so that's what we use. Okay, so this is sort of a grid, like so that we can plot the root locus for the entire range of k. So let's say someone asks us, like to plot the root locus, like for all values of k going from, let's say, minus infinity to plus infinity, right? So this is what we will be doing. All right. So that's the sort of like a grid, like that shows what are the various set of steps, like that we would be utilizing. All right. So now Okay, are there any questions on the material that we discussed today? So I'm going to give you an exercise to do. Okay, so the exercise is the following. So construct the root locus for a negative feedback system. Okay, negative feedback closed loop system. Whose open loop transfer function is, I'm going to give you two systems, two problems to solve. The first problem, g of s h of s is going to be equal to k multiplied by, let's say, s plus 2 divided by s times s minus 2, and k is greater than 0. Okay, that is problem 1. In the second problem, this is s minus 2. Okay. The second problem, the open loop transfer function g of s h of s. Please consider, let's say, k times s minus 1 divided by s squared plus 2s plus 2. Okay, k being once again a positive parameter. Okay, so I'm asking you to do the first set of steps. Okay, in these two problems, that is, like, we have a negative feedback system with positive k. Okay, so please use the first set of steps. Alright, so please do both these problems. So we can immediately observe that in the first problem, value of n is 2 and value of m is 1 in both problems. Right. In the first problem, problem A, we have open loop poles at 0 and 2, and open loop 0 at minus 2. Right. In problem B, we have an open loop 0 at plus 1, and we have complex conjugate open loop poles, right, at minus 1 plus or minus j. Okay, so that those are the differences, okay, between problem 1 and problem 2. Okay, so I think those are the key let's say observations, right, from these two problems. Okay, so please do these problems. Okay, any questions about today's class? Okay, so if not, let me close today's lecture, and then we will continue in the next class.